There are some very unique bodies in the solar system, such as Io with lots of erupting volcanoes, Titan with lakes and seas of liquefied hydrocarbons, Pluto with nitrogen glaciers, the two-faced Iapetus, Miranda with its patchwork-like terrain, and so on. There are plenty of other examples. It's not surprising, especially comparing to those that I mentioned, such an apparently inactive grey rock like our moon might seem boring to many. But this, of course, is far from the truth. The next time you look at the moon in the sky, think about this. Doesn't it seem strange, special? Maybe there's something wrong with it. Meanwhile, it is strange and special, and in a certain sense there is indeed something wrong with it. Conspiracy theorists have some crazy takes on the moon. They might claim that the moon either doesn't exist at all, or it is artificial, or it is a hologram, and so on.
Today we're not going to talk about those things, although one did sneak into this video.
In this video I decided to compile several interesting questions concerning the moon. Is it true that the Earth and the moon are a double or a binary planet? Is the moon the ninth planet? Why is the moon so different from other planetary satellites? Why is it so huge? And why do all the craters on the moon supposedly have the same depth? Maybe it is really artificial. Today we'll talk about all this.
I'm Andrei, and this is Cosmos Elementary.
Our moon is indeed unique in many ways. It is the only satellite of a planet in the solar system. Other planets have either several or many moons, or none at all. It is the only large satellite of Earth-like planets in the solar system. And by the way, did I say that the moon is huge? Well, of course it's not the largest moon in the solar system, it's only the fifth largest. However, the word only might not seem quite fitting once we consider the satellites that come before it. Fourth is Io, then Callisto, then Titan, and Ganymede. All of these are satellites of giant planets. Planets that are many times larger than the Earth, while our moon in comparison isn't significantly smaller than the largest satellites. What makes the moon unique is how big it is relative to its planets. Even the largest satellite in the solar system, Ganymede, is about 26.5 times smaller in radius than its planet, Jupiter. Here's a visual comparison of Jupiter with Ganymede and Earth with the moon. The radius of our moon is more than a quarter of Earth's radius. Such a large satellite compared to its planet is not seen anywhere in the solar system, particularly among the 8 major planets. I'm excluding the dwarf planets for now. Because of its ratio, some refer to Earth and the moon as a double planet, which we will discuss in more detail.
Such an unusual size ratio immediately raises a lot of questions. Why did this happen? What does it mean? Who is to blame?
The reasons for the moon's size are likely connected to how it formed. Its formation process seemed to have been quite unique and different from the formation histories of most satellites in the solar system. In the inner solar system, among the rocky Earth-like planets, there are only 3 satellites. Besides the moon, there are Mars's moons Deimos and Phobos. However, comparing these two potato-shaped rocks with the moon is almost embarrassing. Given their major axis diameters of 16 and 26 kilometers or 10 and 16 miles respectively, compared to the moon's nearly 3,500 kilometers or 2,200 miles. And the remaining hundreds of satellites of planets that are available for comparison are moons of giant planets. Just a reminder, we have to work with what exists in the solar system, because we don't know of any confirmed exomoons yet, moons of planets outside the solar system. There are only a couple of candidates, and they also have been questioned lately.
How do satellites form around giant planets? The primary formation mechanism is considered to be accretion.
And it resembles how planets are thought to form around young stars. A small portion of the material that didn't become a star forms a protoplanetary disk around it, within which planets form. So, systems of giant planets can resemble a star with a protoplanetary disk. Around the planet, from remaining material, there forms a circumplanetary disk where satellites are formed. This is evidenced, for instance, by the fact that many moons of planets are roughly in the same plane as the planet's equator.
Satellites could also be objects that originally had formed somewhere else and later were captured by planet's gravity.
For such moons, their orbits are often highly inclined relative to the planet's equator. Their orbits can be not as circular but highly elongated with a significant eccentricity. These moons can range from small bodies like asteroids to fairly large ones, such as Neptune's largest moon Triton, which is the 7th largest moon in the solar system by size. But the moon, as far as we know, formed via neither of those ways. There are of course other formation pathways, such as a chunk of the planet being torn off due to rapid rotation around its axis. However, as many of you are likely aware, the main version of the moon's formation is the giant impact hypothesis, in which the moon formed from the material ejected into orbit after a Mars-sized protoplanet called Theia supposedly collided with the Earth. So the moon could have formed differently from most other satellites in the solar system. One could naively look at it this way. If we draw an analogy between a star with planets and a planet with moons, we typically see a similar size relationship. Planets are much smaller than their stars, though there are already some known exceptions, such as planets like TOI 5205b or GJ 3512b. These are massive giant planets similar in mass to Jupiter, but orbiting red dwarf stars. Large planets orbiting small stars. Although this doesn't quite fit into modern theories of planetary formation, these cases still need further study to understand how they came about. Also, such discoveries are rare. So in formation pathways like accretion, a large satellite like the moon is unlikely. But through a collision between two bodies, it is conceivable for bodies with the size and mass ratio similar to Earth and the moon to form. However, it's not quite that straightforward either. A paper titled "Large Planets May Not Form Fractionally Large Moons" was published in the journal Nature Communications. I've already said that while we've discovered thousands of planets outside the solar system, we haven't found any confirmed exomoons. And one of the main goals of this research is to aid in this endeavor, to impose certain constraints and to make the search more efficient. First of all, regarding the standard view of how the moon formed, we need to make an important clarification. So, a collision occurred, material was ejected into orbit, and from this material, a disk formed. But what kind of disk was it? It is believed that it was a partially vaporized disk. This means that part of the rock evaporated and existed in a gaseous state, while the other part consisted of fragments of varying sizes, essentially rocks. Next, the author of the study conducted computer simulations of protoplanet collisions to observe what kind of disks and satellites ultimately form from them. This study focused specifically on Earth-like rocky planets and also icy planets, while mini-Neptunes and gas giants were not included in the calculations. Scientists conducted a series of different collisions involving planets of varying masses, and here is what their models showed. Not all collisions resulted in partially vaporized disks. Instead, fully vaporized disks emerged, where large moons could no longer form. And here's why. In those simulations, mini-moons began to form, ranging from 100 meters to 100 kilometers, or 62 miles in diameter. However, in disks with more gas, this gas exerted stronger drag on the mini-moons. As a result, they would spiral inward and collide with the planet, preventing the formation of larger satellites in such disks. Such fully vaporized disks appeared around more massive planets, those with more than 6 Earth masses if they were rocky, or more than 1 Earth mass if they were made of ice. And this happens because collisions involving more massive planets release more energy, allowing the material to become fully vaporized. If the scientists' conclusions are correct, this will help to search for exomoons more efficiently, for example, focusing on Earth-like planets with masses less than 6 Earth masses. If you want to find a large moon, which theoretically should be easier to detect. Another implication is that it is believed that the large moon is an important factor in creating conditions suitable for life on Earth. The moon stabilizes Earth's axial tilt, influences the climate, and is generally considered very important for life on Earth. But returning to our topic, the conclusion of the study in some sense makes our moon even more unique. I've already mentioned that we have a large moon due to how it's formed. Now we see that even the collision model does not guarantee a proportionally large moon. And for rocky planets, this may be only possible with a certain range of masses. Well, what about the idea that the moon and the Earth are a binary planet? In 2003, the European Space Agency website featured a publication titled "Moon, Welcome to the Double Planet." The article itself discusses the first European spacecraft to the Moon, SMART 1, launched in 2003. But it also asserts that the Earth and the Moon are not just a planet and its satellite, but a double or a binary planet. What arguments are presented to support this claim? Firstly, the ratio of sizes between the Moon and Earth, which we have discussed in detail.
Secondly, that's basically it. Size is the only argument.
But it's not exactly a scientific paper. However, statements about the Earth and the Moon being a double planet on the official website of one of the largest space agencies in the world could lead many to believe it's set in stone.
Although, in reality, it's all quite murky, and of course, such considerations were made much earlier.
Firstly, it's worth noting that whether something is considered a double planet or not is essentially a matter of terminology and how we agree to categorize pairs of celestial bodies. If we want a clear answer, we need equally clear definitions of what a satellite, a planet, a double planet are. Such terminology is defined by the International Astronomical Union. It has provided a definition for what a planet is, though many have questions about this definition. That's the one official definition that in 2006 stripped Pluto of its status of the ninth planet of the solar system. Let me remind you that according to this definition, for a body in the solar system to be called a planet, it must meet 3 criteria. Here is the actual resolution, and according to it, a planet is a celestial body that A. is in orbit around the Sun, B. has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round shape, and C. it has cleared the neighborhood around its orbit. It was precisely the third point that deprived Pluto of its planetary status. But here's the catch.
What does it mean to clean the neighborhood around its orbit?
In this case, it turned out that besides Pluto, in that distant region of the solar system, there are many similar objects on similar orbits, and there are even some comparable in size to it. It's like if there were several more Mars-like objects in the vicinity of Mars' orbit.
However, what exactly is the neighborhood? How far from the orbit? What does it mean to clear it? To make sure there are no objects at all?
So by this criterion, Earth wouldn't qualify either, because there are some near-Earth asteroids on similar orbits, and Jupiter with its groups of Trojan asteroids, but it's clear that comparable-sized objects are meant. But in the actual resolution, this is not explicitly stated anywhere, so some still criticize this definition to this day. The first of the terms we need is already causing some problems. Next term, double planets, or again binary planet. What clear criteria must a system of 2 bodies meet to be called a double planet rather than a planet-moon system? Well, the International Astronomical Union doesn't actually provide such a definition. In fact, they don't even provide a definition for what a moon of a planet is. So if we want to confidently label Earth and the Moon as a double planet based on clear regulations and documents, we won't be able to do that. Perhaps such definitions will appear someday, but they don't exist yet.
However, there are some less official discussions and individual opinions where some specifics can be found. For example, you might come across a criterion that is based on mass.
It goes like this. If two bodies share an orbit around a star and orbit each other, the larger one is a planet and the smaller one is a moon. But if their masses are equal, meaning the ratio of their masses is close to 1, then they would be considered a double planet. However, this scenario is highly unlikely. More likely their masses would differ, and in such cases, many would classify the smaller body as a moon, even if its mass is only slightly less, perhaps even just by 1%. The ratio of radii of Earth and the Moon is approximately 1:4, or more precisely 0.27. But the mass ratio of the Moon to Earth is 0.0123, meaning the Moon's mass is 81 times smaller than the Earth's mass, so we are far from 1:1 ratio here. However, again, this is not an official criterion.
Another factor that is often discussed is the location of barycenter, or center of mass, a point in space which both bodies orbit around.
Binary systems that are regularly encountered and where there seems to be no disagreements or doubt in their definition are binary stars. In such systems, the two components can have vastly different masses, but it's not uncommon to find binary stars where the masses of both stars are comparable. Let's say a pair of two red dwarfs, or two sun-like stars, and so on. For the sake of simplicity, let's consider two stars of equal mass. Assuming their orbits are not elongated, the system would appear like this when viewed from above. Here is the barycenter. Both bodies orbit around it, although it is essentially just an empty point in space. Here is a more realistic scenario for binary stars, as their orbits are often elongated, but still the barycenter remains in the empty space. When the masses of two bodies differ significantly, things are different. In the Sun-Earth system, the barycenter is inside the Sun. Specifically, considering how much less massive Earth is, the barycenter is very close to the center of the Sun. So for defining through barycenter, some suggest calling a system a double planet if the barycenter is not inside either body but in empty space around which both bodies orbit, similar to examples with stars. By the way, there is a system in the solar system that fits the definition. This is the system of Pluto and Charon. Although Pluto is more massive, Charon is substantial as well, when the center of mass of the system is outside Pluto's surface. Their mass difference is also not as significant as between Earth and the Moon. It's only 10-fold compared to 81-fold. The barycenter of the Earth and the Moon is not located at the center of the Earth, but rather quite far from it. It is closer to the surface, and given the Earth's average radius is 6,371 kilometers, or about 4,000 miles, with the barycenter situated approximately 4,650 kilometers, or about 2,900 miles away from the center. However, it is still within the Earth, and not outside of it. So by this criterion, the Earth and the Moon do not qualify as double planet again. Pluto and Charon would be a closer match. Their barycenter is outside of Pluto, and the mass difference between them is not as significant compared to Earth-Moon system.
But the issue with Pluto is that, at least according to the resolution from 2006, it is not considered to be a planet at all. So how can it be a binary planet when it is not even a single planet?
There is no official definition of a double planet, and there are no clear, universally accepted criteria. According to unofficial criteria, Earth and the Moon also do not seem to qualify as a double planet. But while I was researching various sources, I came across an interesting twist. I found an opinion, and not just any opinion, but a paper published in a scientific journal. Though there's a little caveat there. The article suggests not calling Earth and the Moon a double planet, but simply referring to the Moon as a planet, the 9th planet of the solar system.
And you are like, what? So let's see what it's all about.
Here is the paper published in 2017 in the International Journal of Astronomy and Astrophysics. It's called "The Moon Meets All Requirements of the IAU Definition for Planets."
The paper firstly discusses a lack of criteria and clear definitions for things like binary planets or a moon of the planet that we have already discussed. Additionally, it claims that the moon meets all three criteria.
Well, from obvious points, actually it does meet the second requirement. It is massive enough to have a spherical shape. This criterion, however, applies to Pluto as well, but with other two requirements it is not that obvious. In the case of clearing neighborhood, here most of work has been done by the Earth. The article states that the Moon is massive enough to clear its orbit in the Earth-Moon system, but initially it seemed that we weren't talking about that. But the main requirement is about the orbit. The body must orbit around the Sun. And here, instinctively, one might want to say that the Moon doesn't really orbit the Sun independently, but rather orbits the Earth first. However, there is a catch. What does the Moon's path around the Sun look like? Someone might think that it looks like this, and they will be incorrect. Others would imagine this, but considering the scale, it is also not very accurate. Let's look at the trajectory of the Moon in the universe in box. Here, at least the scales are more or less preserved and the motion is shown correctly. So the Moon moves forward along Earth's orbit, and its trajectory changes slightly. Sometimes it's on one side of the orbit and other times on the opposite side. The white line represents the Moon's trajectory, and we can see that it deviates slightly from the blue line, but we don't see any loops, like in this image. This image essentially shows the same thing we just saw in the universe in box. The blue line represents Earth's trajectory, simply moving in an ellipse around the Sun. The Moon's trajectory around the Sun is shown in yellow, and it closely follows Earth's trajectory, with Earth only causing slight variations in its movement. Here the Moon is slightly closer to the Sun, and there it is slightly farther away. In comparison to the distance to the Sun, this difference is barely noticeable. If we zoom out, the trajectories would basically merge into one. So in the Sun's reference frame, it seems like the Moon is actually moving more along an orbit around the Sun rather than around the Earth. Earth only slightly perturbs the Moon's orbit, and they travel together. But then, if we follow that logic, does this mean that any moon of a planet, like Europa or Titan, viewed in the Sun's reference frame is also considered a planet? However, the author of the paper has an answer to that question as well. The Moon is influenced by the gravitational pull of both the Earth and the Sun. But the question is, which is stronger? It turns out that the Sun's gravitational pull on the Moon is approximately twice as strong as that of the Earth, while the same comparison for moons, for example, of Jupiter, is actually in favor of the planet. There, the moons are more under control of the planet, whereas the Moon is more influenced by the Sun. This distinguishes it from other moons. So according to the author, the Moon fits the criterion of must orbit the Sun, and its orbital neighborhood is reasonably clear as well. Therefore, all three criteria apply, so we should consider the Moon to be the 9th planet of the solar system. So the arguments are interesting, but so far no one has rushed to rename the Moon as a planet. I mentioned that there was a caveat in the story, so perhaps the journal in which this article was published also plays some role. Scientific research publishing does not have the best reputation, and it is included in the list of so-called predatory publishers. There have been a couple of scandals associated with it.
Why did the author choose to publish the paper there and not in some more prestigious journal? This fact alone doesn't nullify the arguments, but it does make you think.
However, what even this research shows is that there is indeed some ambiguity in definitions, and it would be better for International Astronomical Union to clarify them. Now let's do something a little different. So conspiracy theorists like to speculate that the Moon is artificial or hollow inside and so on. And one of the arguments they bring up is that the craters are supposedly strange. One such supposed strangeness is the depth of craters. For example, here is a random article from the internet with arguments in favor of the artificial Moon. So here it is. Shallow craters. They say, why all the craters on the Moon the same depth, whether they are small or huge, with diameters ranging from tens to hundreds of kilometers? In their logic, wide craters should be proportionally deep, but we don't see that. Something doesn't add up here. What conclusion can be drawn from this observation? Well, in this article, the conclusion is that the Moon has a relatively soft layer of regolith on top, which can be penetrated to a certain depth. And beneath it lies a much stronger artificial metallic sphere. But the problem is that the craters are definitely not all the same depth, and they aren't really that shallow either. The depth of some large craters reaches several kilometers. Take the crater Tycho. It has a depth of almost 5 kilometers or over 3 miles, and there are even deeper ones. At the same time, small craters have depths of only few tens of meters. How can one say that they all have the same depth?
But you get the idea of what people mean in this case. Indeed, as the diameter of craters increases, the ratio of width to depth changes. The larger the crater, the smaller this ratio becomes.
For the 85 kilometer wide Tycho crater, this ratio is approximately 1 to 18. Generally, for large craters, this ratio varies from 1 to 15 to 1 to 25. So large craters in shape can be compared to a flat plate, while craters of smaller diameter resemble more of a deep bowl in shape. So why are large craters so shallow compared to small ones? To form a crater 10 to hundreds of kilometers in diameter, a very large object is required. In such collisions, a tremendous amount of energy is released, and solid rock behaves similar to a liquid. For the same reason, craters are mostly circular, and their shape doesn't generally depend on the angle of collision, because it is the explosion that makes the crater. Here is a simulation of a collision between a 10-kilometer asteroid and the Moon. We see how the rock behaves. It's more akin to how the surface of a body of water reacts when a stone falls into it. And the indentations in the water don't last long as well. And here is a simulation of the formation of the largest known crater on the Moon, the South Pole Aitken Basin.
Those who use that argument apparently believe that
crater formation must stop at this stage. But where will all of the energy and motion of the rock go? And also, if you know anything about gravity. Do you remember one of the criteria in defining planets? The body must be massive enough for its own gravity to pull it into a spherical shape. When bodies reach a certain threshold of mass, they naturally tend to assume a spherical shape. Small asteroids are irregularly shaped, whereas larger bodies tend to be spherical. So the gravity of the Moon simply wouldn't allow such a crater with a depth of a significant fraction of the radius of the Moon to persist for long. Gravity corrects the shape. Obviously, the shape of any large body is not perfectly smooth, and there is terrain and mountains both on Earth and on the Moon. However, bodies in hydrostatic equilibrium have certain limits regarding the depth of basins and the height of mountains.
what I appreciate about the conspiracy theorist questions, although not everybody who is asking those questions is a conspiracy theorists. Some people genuinely want to know. But sometimes those questions give us a reason to talk about how things really work.
In general, no matter what anyone says, I could never bring myself to call the Moon a dull gray rock. Even though I've talked about it quite a bit already, there is still so much more interesting about it. If you enjoy these kinds of videos, let me know, and I will make more.
Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment, subscribe, and feel free to share this video with your friends if you really liked it, so I can get a little more views. As you can see, I don't get many. So thank you for watching one more time, and bye bye.